Hello everyone, welcome back in the course of Higher Surveying. Today we are in fourth lecture of module 8. In the lecture 1 and 2 we have learned the geometric aspects and radiometric aspects of the radar image. In the third lecture we learned how to obtain the topographic information using the radar images to create the 3D model. And that's why we said the name of the particular lecture as radar grammetry. Today we are going to talk about interferometry or radar interferometry. What is the connection of the interferometry and radar? You can recall the simple concept of interference. So if you remember the 11th or 12th standard knowledge, we say that if there are two waves in the same phase, we will have constructive interference. But if the phase difference is pi or half of the wavelength, then we will have destructive interference. Also, in our experimental classes of 11th and 12th standard, we have seen this interference phenomena for the optical waves or optical light. I hope that you can recall those things again. Well, here the context is similar but not the same. First of all, the radar image is a complex image. That means it has quadrature component and it has phase component. And using quadrature and the phase component, we calculate the magnitude. Now, instead of using the quadrature component, we want to use the phase component of the radar image to measure the height of a point. That means if the height of a point or the position of a point changes, still I can use the interferometry. So in this lecture, we are going to talk about all these aspects. First, we will discuss about the technical perspective of the interferometry and how is it used in order to measure the height or the range difference. So let us go ahead and delve into this lecture. So this is the fourth lecture and again books are same. So let us introduce what is the radar interferometry. As I told that radar records the complex images. So in case of interferometry, we record the phase and using the phase we calculate interferogram that we are going to discuss in this lecture as we proceed. So interferogram is then used to derive the minute differences in the range measurement. So that's the logic here. We can find out that the SAR interferometry can deliver high resolution topographic maps. It can be used for velocity mapping and it can also be used for the change detection. And we are going to learn all this in this lecture. Let us consider phase of the radar. If you remember, we said that synthetic aperture radar or the radar we are going to discuss in this module is only valid for the coherent backscatter. That means one radar sensor is throwing some pulses and it is recording the backscatter. The backscatter is also coherent. Now you can imagine that there are two radar sensors and each is recording the coherent backscatter for one point on the terrain of Earth. What is the game here or what is the logic here? We know that if there are two radar sensors which are at different position, the range from each radar sensor will be different for the same point on the Earth. So whatever information they capture about the point, from that information, that is the phase information, we will derive some kind of logic and that logic will be equipping us to derive the difference of the range of the two radar sensors from the same point on the Earth. After finding out the difference of the range, I can also find out what is the height of the point. So let us look into this aspect here. Let us say that we have same phase for a sensor here and then two different sensors have different coherent phases for a point on time. So here let us represent phase information by this complex image and here we are representing this psi 1 which is a phase here. So psi 1, it is coherent phase recorded by sensor 1. And then we have psi 2, the phase recorded by the radar sensor 2, or I can say here both sensors are same or both radar sensors are having the similar or same properties. Phase phi 1 here can be represented as 2 pi upon lambda into the distance traveled which is 2r here. So I am writing it here like this and j is minus 1 and under root here. E2 for the other sensor, if I am observing the phase phi 2 for same point and I know that the distance from another sensor or the sensor number 2 is r plus delta r. So delta r is change in the total range 2R. So first we have 2R range, and now we say that from the next sensor we have 2R plus some difference in the range. So we are writing like this. So this is complex image and this is another complex image for a point on terrain, or I can say for 1 pixel that is acquired on the terrain by radar. So this is the one information. Now take the complex conjugate of E2, which is E2 star. It's E j psi 2, and I put minus sign over there, and it becomes E2 power plus j 2 pi, and then we have 2R plus delta R divided by lambda. I am getting the same expression here. So now multiply the E1, that is first complex image of 1 pixel, and that is the another complex image. So if we multiply this pixel to pixel, for each pixel I will get this phase difference by simple algebraic sum for exponential here, and as a result I get this expression where I am cancelling the 2R with this 2R, and then we will get this expression. You can do it yourself. You can see here that delta phi, which is phase difference here, is equal to this quantity, and I am writing it here. If I measure the phase difference of the two complex images of radar, where each image is acquired by the same sensor, or sensors can be two, but both sensors should be same. So then it will be equal to this, and so using this expression I can estimate what is the change in the range, and by this range difference I can also estimate what is the height difference of the point. So that is the basic fundamental logic of the interferometry, and that is the application of the interferometry. I hope that you understand what is the phase principle, and so I am writing in words that phase difference is 2 pi divided by lambda, and the path difference. So delta R is path difference between the paths of two radar sensors. So one is having 2R path and another is having slightly different from 2R. So that is 2R plus delta R. So now we have interferometry, and that is called INSAR, that is interferometry synthetic aperture radar, is also called INSAR or IFSAR. That means we are using the interferometry for the mapping, and for that purpose we use the word INSAR or IFSAR. INSAR is of two types, single pass type and two pass type. And then we have another mode called differential interferometry SAR, that is 3 pass type, and it's also called differential interferometry synthetic aperture radar or DINSAR, or sometimes DINSAR. Before we go into the single pass, 2 pass and the 3 pass type, or the differential DINSAR, IFSAR or INSAR, let us first look into the important definitions or important terms here. First is spatial baseline. So let us assume that there are two radar sensors indicated by my fingers here. One radar sensor is located here and another here, and both are observing the same point on the terrain at the same time. That means there is no time difference in their observation. So we call the temporal baseline is 0. That means the time at which both are observing is same, so there is no time difference in their observations, and that is called the 0 temporal baseline. Now here if you see that there is a clear difference of the distance between the two positions of radar sensors, and this difference is called the spatial baseline. I hope that you agree what is the idea of spatial baseline and temporal baseline. Now imagine the other situation. Let us say there is a radar sensor which is revolving around the earth in maybe an airborne or maybe spaceborne, but it is basically observing a point at different times. That means at a certain time interval, what we call the temporal resolution of the sensor. So after one temporal resolution, it is again observing the same point. So I can say here that this is baseline related to the time, or it is called the temporal baseline. So we should understand these concepts very nicely, because we are going to use these terms again and again in different cases. For example, single pass, double pass or 2 pass, and the triple pass or 3 pass. So what is a mixed baseline? When both the spatial baseline and temporal baseline exist together, it's called mixed baseline. Now imagine one case. The radar sensor tracks are identical, exactly the same. Let us say there is a radar sensor, it is moving like this and again coming back to the same point. Well, if the point is exactly the same, what we can say about that? There is no change in the distance between the two radar sensors or the two locations of the radar sensor for the acquisition. Now you can see here that temporal baseline is non-zero, but the point is same. I can say that spatial baseline is 0. I hope you agree with the idea of spatial baseline, temporal baseline and the mixed baseline. Now consider the single pass interferometry logic here. We record the phase of the echo from the target, that is the terrain point, in 2 channels mounted on a platform. This is radar sensor where I am using the one transmitter, but there are 2 receiver antennas, 1 and 2. The difference between the 2 receiver antennas is called the baseline or spatial baseline. This is point on the terrain surface. There is a transmitter. It is transmitting the radar pulse, and radar pulse is traveling for a distance, let us say r. After that, it is reflected in the form of backscatter, and that backscatter is received by the 2 antennas or 2 receivers. And you can see here the simple logic that while transmitter has transmitted the radar pulse, it is traveling the same distance for both the receivers. However, the reflected backscatter which are received by the 2 sensors have different paths, because transmitter is same and we have the 2 different receivers. So here and try to find out the change in the ranges or the slant ranges for the return path only. So this is logic of single pass or simultaneous baselines, and 2 radars acquire data from different vantage points at the same time. So receiver 1 and 2 acquiring the data at same time but at different locations. So we have the spatial baseline. Now I can easily write this relationship here, delta phi equal to phi 2 minus phi 1. If I write range R2 for the sensor 2 and R1 range for the sensor 1. So I am writing the difference of the 2 ranges. Now you can see here that there is a common path between the 2 receiver antennas, so we ignore that, and hence I can write here that R1, both are only return path. Here we introduce a factor called P such that I can write very generic expression for all the cases, whether it is a 2 travel path, that is R and again R, or it is one path from the target point to the receiver. So I can write 2 things. So I am saying that P here is equal to 1, but in case if I consider the 2 path, that is from transmitter to target and target back to the receiver, so that will be 2 path travel. So in that case I will take P equal to 2. If I have 2 radar sensors, that means each radar sensor have the different antennas or different receivers. I need to consider the complete path from transmission to reflection back to the sensor. In that case P will be equal to 2, because we have traveled double distance from transmitter to target point and again target point to the receiver. So that is for the radar sensor 1. Similarly, same thing happened for radar sensor 2. In that case P will be equal to 2. Once we determine this phase difference, we calculate this quantity psi m, and psi m is the mode of the delta psi or 2 pi. That means I am reducing the delta psi in the range 0 to 2 pi. Now for each pixel, if I plot this value on the radar image, this image is called interferogram, and that is the difference of the phases. I hope you got the idea now what is interferogram. First we estimate the range difference of the 2 points from 2 different locations of sensor, and using this range difference delta r, I can find out the height of a point. Interferogram records psi m information, which is modulus of the observed delta psi. So let us go for derivation. There are 2 antennas 1 and 2 here, and the baseline between the 2 is indicated by r21. The length of the r21 vector is equal to the baseline here. You can imagine that there is a sensor like this and there is an antenna. So one antenna is there at this location and another antenna is this location, and sensor is moving in this direction like this. Both sensors or the receivers are observing a point on the surface of Earth. Let us say this is a point, so it is being observed by this receiver antenna and this receiver antenna. You can imagine that this is the way we are observing different points. This is length is called baseline. Now you can see this is the across the track direction yp, and this is along track direction, which is not shown here. I know that point 1, point 2 and point P, they are in one plane, as you can see here, like this. This is range R1, this is range R2, this is the angle theta 21 and this is the angle theta. Theta 21 and theta look angles for point P by the different receiver antenna here. Now I can write from this triangle 1, 2 and P that R2 square, which is this distance, equal to R1 square plus B square, this is B length here, minus 2 R1B cos of theta 21 minus theta. So basically I am saying that this angle is theta 21 minus theta, and I am using the cosine rule to write the R2 in the form of R1 and B. I hope you agree with that. If I do some kind of small transfer on left and right side, I will get this expression R1 square minus R2 square plus B square divided by this one equal to this angle. We know here that theta 21 is pi by 2 plus alpha. This is the horizon here and this is the another direction. So I know that this angle is 90 degree here between the horizon and nadir. So I write pi by 2 plus alpha. So this angle is alpha here. So now if I replace this thing here, what will I get? I will get this expression, and from that I will get this one. So you can look here that this is theta angle here because it is equal to this angle, and the point P is having a height HP here that I want to estimate. Let us write this one there like this and here. Again on the right hand side there is some approximation. Let me write R1 square minus R2 square as R1 plus R2 into R1 minus R2 plus B square divided by 2R1B. We make an assumption that R1 and R2 are approximately equal. As a result, R1 plus R2 approximately equal to 2R1. The expression here comes sin theta minus alpha equals to, this is 2R1 and this will be cancelled by this. So I have R1 minus R2 divided by B plus B square upon 2R1B. So it is cancelled here. So this is B upon 2R1. Now if you see that baseline is in order of 2 to 3 meter. So the R1 distance is very high in kilometers, maybe some 100 kilometers or so. So this B by 2R1 here is equal to 0 or very small value. I have this expression R1 minus R2 divided by B, which is sine of theta minus alpha, and which is written here. I hope you got this idea. So what is theta here? Theta is look angle. What is the alpha? Alpha is this angle, which I already know by design criteria. That means when we design sensor, we know this alpha angle. Now I can find out the exact value of the look angle, the theta. And so the theta is written like this. Before that, remember the phase difference R2 minus R1 is equal to delta R. Here we know that delta psi is equal to, in case of single pass interferometry, 2 pi upon lambda into delta R. Delta R, which is R2 minus R1. So I say that delta R, which is R2 minus R1, is delta psi into lambda by 2 pi. And if I take R1 minus R2, then it becomes minus delta psi into lambda upon 2 pi. So I replace this value over there, I will get this value. You can see here, again I am putting the factor P here for different cases. So P factor we have assumed here 1, but still for the general case I am writing P here. Finally, this is look angle value. Here this flying height h and minus this HP, this distance is R1 sin theta. So this is expression here, and y is another coordinate in across track direction, that is equal to R1 sin theta. So now I have find out the coordinate of point P on the terrain using the single pass radar interferometry. Let us look into the performance limitations. So what are the limits of the performance of single pass radar interferometry? There is a signal to noise ratio, and we measure the radar image using the signal. So we have signal to noise ratio, and that is giving 1 sigma precision value of phase difference measurement or the interferogram measurement. From there we can write this expression that given the sigma delta phi, what is the value of sigma theta? That is the 1 sigma precision of theta value, that is the error in the look angle. So we get this expression here. You can do it yourself, because we have sin theta minus alpha is equal to lambda delta psi divided by 2 pi p b. From there, by using the error propagation, you try to find what is by sec theta, you will get this expression. Now we can see here that the theta is equal to alpha minus sin inverse, some expression was there. So if I just assume that all this information is given, I can write that sigma theta is equal to sigma alpha. That means given the values of alpha, what is sigma theta? That is sigma alpha, which is error in the baseline angle. Baseline angle is the alpha angle. Here then we write using the same expression of the r, h and y. So what is the error here? Given this error sigma theta, I get r sin theta into sigma theta, and sigma y theta is equal to r cos theta sigma theta. So here I can estimate the sigma theta by two logic. This is one and this is another. So which one I will take? For the worst case accuracy, I should take the higher of the two values. So let us look into a simple exercise of the numerical here. Signal to noise ratio is the 20 decibel. Baseline is equal to 2.5 meter. Lambda wavelength is equal to 5 centimeter or 6 gigahertz. Then we have theta is equal to 45 degrees, that is look angle, and we have the flying height equal to 13 kilometers above the earth surface, and then we find out sigma theta is equal to this value. This is the value given to us. So what is the value of range? That is h upon cos theta, and so I write 1 upon root 2 here, cos 45, and here h is 13 kilometers. So here I get 18384.78 meter. Let us calculate the error in the height given the value of theta, r sin theta into sigma theta. So here r is 18384.78 into sin 45 into sigma theta is in the radian form. I can write 0.018 degrees divided by 180 into pi into radians. So this is radians. Now I can find out that this value comes out to be 4.08 meter. At the same time, what about the sigma y theta, r cos theta sigma theta, and if you put this theta equal to 45 degrees, we have this also equal to 4.08 meter. So that's kind of a realistic estimate of height and the error in the height. So the error in the height will be around 4 meters. So we should not expect very high level of accuracy when the height accuracy itself is 4 meters. Where this accuracy is useful? Now imagine there are some global phenomena. For example, landslide has occurred, and there was a so severe landslide that few meters land has passed. Now if I use this data, which is 4 meter accurate in height measurement, and the height measurement is say 20 meters. So this 4 meter accuracy is good enough for that purpose. Or imagine something, a building has demolished completely which is of 100 meter height. Now if I use the 4 meter data, that's absolutely fine. We should know about what are the realistic aspects of resolution here. So this is some idea about the performance limitation. One more aspect we can address, and this aspect is related to the baseline. Imagine that if there is a baseline between the two receivers, if it is increased, what will happen? The term b comes into the denominator of the 1 sigma value of accuracy of theta. So accuracy is inversely proportional to the baseline length. Higher the baseline, I will get superior accuracy. With this aspect, there is a limitation to which we can increase the baseline. What could be the most optimal value of the baseline? And that is called a critical baseline length. That means we can increase the baseline length up to that limit, beyond which there is no point. So let us look into this aspect. So first of all, let us say that we know if across a pixel or the range resolution, or what we call a pixel on the ground surface, if psi value or phase difference changes by minus pi to pi or 0 to 2 pi, that is the maximum possible value I can have. Corresponding to that one, which we call critical baseline, because a baseline that can create that much of difference could be the maximum possible value of the baseline. So that is what we have to now consider. So let us define fringe rate. What should be the rate of change of phase angle with respect to the range, such that it should create a phase angle by 2 pi. So what I am saying is, let us say if there is a range resolution, over this resolution, if the phase changes by 2 pi angle, which is 2 pi minus 0 difference, that means that is the best possible range for which I will have maximum change in the phase. So how can I write it? First of all, one should know that d psi by dr is d psi by d theta and d theta by dr. So now you put the values of these variables from the previous slides, you can differentiate it partially and then you can put it. Once you put it, you will get this value, and that is called the fringe rate. Now we want a change in the phase such that over 1 pixel resolution it should be maximum, which means if I multiply that d psi by dr, this fringe rate, with 1 range resolution, I should get it equal to 2 pi, which means if I put this value here, then what will I get? I will get 2 pi pb divided by lambda into cos of theta minus alpha divided by r tangent theta into the delta r, which is this here, should be equal to 2 pi. This is the way we define the critical baseline. So let me write b is equal to as critical baseline here. First of all, let us remove this common factor 2 pi. So the critical baseline BC is equal to r tangent theta lambda divided by p cos of theta minus alpha and delta r over here. I can write here r sin theta lambda divided by p cos theta minus alpha into cos theta into delta r here. Now we know that the delta y, that is the ground resolution in across track direction, is given by delta r upon sin theta. So we have written BC is equal to r lambda divided by p cos theta minus alpha sin theta divided by cos theta delta r. So by replacing the value, we can write here BC is equal to r lambda divided by p cos of theta minus alpha and cos theta, and then here delta y. One nice expression I can write here. Let us multiply this b to cos of theta minus alpha, and here it is equal to r lambda divided by p cos of theta delta y, and this term is the projection of baseline BC in the horizontal plane or normal to the track direction. We write here BC perpendicular or orthogonal to the loop direction is equal to BC cos of theta minus alpha is equal to r lambda divided by p cos theta delta y. Now we want to determine the phase also, because using the phase information we have determined the height. So we have basically converted a phase delta psi into psi m. Now I want to recollect this information from this. So that is called phase unwrapping. And for phase unwrapping, there are many algorithms available. Someone who is really interested in phase unwrapping should refer to those algorithms. So that is absolute phase difference. We have discussed the single pass interferometry in detail. Now let us consider the two pass interferometry. What are the important issues here? There is radar sensor which is moving on a certain orbit or track, and there is another radar sensor which is moving like this. So they are observing a point on terrain of Earth at different time automatically. Since they are moving on a different tracks, spatial baseline exists as well as temporal baseline also exists. So that is the important issue we have highlighted. So a point on terrain is observed by two radar sensors. That means even I have two radar sensors in different paths, or there is one radar sensor which is having some temporal resolution and which is coming in the next path at different path. So then we have temporal baseline exist. I'm sorry, it should be exist, but no change in the terrain point. Now we have unknown spatial baseline. Tracks are not parallel of the two radar sensors. So it will lead to some difficulty in finding baseline. We have assumed that there is no change in the target area. Suppose there is a change. For example, we are trying to study the glacier, and glacier is melting. What will happen if there is a big rock mass is there on the glacier surface and glacier is moving? The point that is rock mass will also move. That we assume that there is no change in the position of the point, and that is wrong assumption. In this case, we have to consider the temporal decorrelation. What about the motion compensation? In case of aircraft, it is slightly difficult. So the estimation of the baseline is very, very difficult here in case of two-pass interferometry. But let us look into that. How do we do it? This is two-pass interferometry, and we have radar sensor 1 here and radar sensor 2 here, and both have different receivers. So now we should consider p equal to 2 if we are considering the two paths here. This is path is different and this path is different. Total range should be considered from this point to this point here. Similarly, for this antenna, from this point to this point again, total range of travel should be considered. So it's called repeat pass or the repeat track. So I hope you got the idea that this point is under observation, and this is the baseline now. Let us say there is a one track here, and this is satellite over there, and it is observing a point here, P on terrain, and there is another track here. From here, again there is another radar sensor. So let us say sensor 1 or sensor 2 here and sensor 1 here, and it is also observing the point here. Now it could be different path, or even one radar sensor can come into the different paths. I want to estimate the baseline. Let us assume that there is another point and which has some reference frame here, x, y, z. This is z here, and this is x which is along the track direction here. This is x and this is y. Now you can see here that if it is 0, 0, 0, and if this is flying height h, with another point here, if I drop here like this, so this another point has coordinates, let's say x0, y0 and z0. Because of this flying height which is here up to, so this is point here, this point is having coordinates x0, y0, z0 plus h, and this is baseline now. And since the tracks are having different orientation, I have to match tracks first, and then I will estimate the baseline by estimating the difference between the two parallel tracks. So this is track 1 here, and this is another track which is not parallel. I will orient this track in a way that it becomes parallel to this track, and after that I will find out the distance between the two parallel tracks. So that is the way we determine the baseline in case of two-pass interferometry. This logic is there. I have written the position of R1. This is R1 here to here, this vector, and this vector is R2 here. I write it R2S. This is R1S. So now this is R1S1. So I am writing 00H plus this S1 is pulse number and delta X is the along track pulse spacing. So for one pulse spacing, I have delta x. For S1 number of pulse spacing, I will have this distance. So then I am writing 1 0 0 here. That is R1 vector. Now what is R2 here? R2 is this coordinate of the second sensor, and then this is the distance here. This distance is first calculated to the dy by dx, that is the track change or track divergence in y direction. So if I consider this track divergence, I have put the correction by this amount, that is S2 delta x into dy by dx. Similarly, I have put corrections for the track divergence in z direction like this, and then I know that both tracks are parallel. So there is only a difference of the distance. Now I say that the track 2 is having some scale factor, and as a result this scale factor is gamma 2, which is less than 1. So it's 1 plus gamma 2 is total differential factor. So by this way I have estimated R2, that is the position of the radar sensor 2 in XYZ system. Now both tracks are in same coordinate system, and if I take the difference of two vectors, I can find out the baseline length. So that is the idea here about the two-pass interferometry. Now let us look in one application of two-pass interferometry, and that is the velocity mapping. Remember, I said that during these two passes we assume that the point is not moving on the terrain. Now assume that there is a glacier and glacier is moving, and because of that the point is also moving. In that case, when the radar will come on the next pass, during that time, what we call, let's say, delta t time, the point has moved. So both the radar sensors will be observing different points for the same feature, and by observing these two paths, I can find out what is the velocity of the movement of the point. So that is the one application of the radar interferometry. So let us say if I measure the phase here, the psi, this is delta t time here, and this formula is given. This is the delta t time during which that point has moved. So once there is a radar sensor here, and in the next pass or in the next time when radar sensor comes, it finds that the point has moved. Now I can see that radar sensor is moved by a distance d on a trajectory during this time delta t. I can write this delta t is equal to d upon v here in the same expression, where u is the radial target velocity on the surface of earth. Moreover, we assume here that the velocity in the vertical direction of terrain point is 0. So I get this expression. Here I find out the u from this equation, and by putting the value of u here, I can find out what is the value of the velocity of the terrain point in y direction or in across-track direction. So that is the application called velocity mapping here. Now let us look in differential interferometry. In case of differential interferometry, we want to find out the change in the position of the point. Let us say there is a glacier, as we have already discussed. We have already shown that how to use the two-pass interferometry in order to measure the velocity of the glacier. But we are measuring the velocity of the glacier on the some datum surface, where we assume that there is no height of the point. But here we are saying that we want to find out the topographic changes in the surface point on the surface of earth. So this point has some elevation. So it is not on the datum, it is situated somewhere up. Moreover, we see that once we observe that point from sensor location 1 and 2, there were no change. The time duration between the sensor location 2 and the sensor location 3, that point has changed its position. So this duration between the second observation and the third observation could be of any magnitude. It could be 1 month, it could be 1 week, it could be 1 year, or maybe it depends on the phenomena. In case of landslide, it could be very small duration, or in case of glacier melting, it could be 1 year also. What do we do basically? We create the one baseline between the sensor 1 and 2 and another baseline between the sensor 1 and 3, because we know that changes happened after the observation from sensor 2. First, we need to understand what is the contribution of the topographic changes with respect to the datum. So what is the correction we need for the earth? And we have a datum here, this datum, and the real terrain is like this. this is the nadir position here of the sensor, and this is the range which has been observed here. Let us call the range as R, and so this was angle alpha as before, this was look angle theta. Now, if I image this point here with the same range R, so it will be imaged here like this. So, this is also R, but this angle is theta 0. That means this point A, if it is situated on the datum, I could have got the angle theta 0. So, let us see the angle difference is delta theta. So, theta and theta 0 are look angles. Now, I can write theta is equal to theta 0 plus delta theta. So, theta 0 corresponds to the point which is on the datum, and delta theta is a variation, and theta corresponds to the look angle of point A on the real terrain surface. Now, if you remember, we have written the delta psi as minus 4 pi by lambda baseline b sine of theta minus alpha. I want to know what is the correction in delta phi I should apply if the point A lies on the datum, let us say A dash. So, if point lies at A dash, I can write here delta psi 0 is equal to 4 pi by lambda b sine of theta 0 minus alpha. Now, if I take the difference of the two, that means delta of delta psi, which is difference of delta psi minus delta psi 0, I will have 4 pi by lambda sine of theta minus alpha minus sine of theta 0 minus alpha into b. Now, I can write it 4 pi by lambda b into sine of theta 0 plus delta minus alpha minus sine of theta 0 minus alpha here. We can expand this term by sine formula. So, I can write it b sine of theta 0 minus alpha plus delta theta minus sine of theta 0 minus alpha. So, I can expand this term by sine formula where this is one angle and this another angle. So, let us look into the next slide. Delta of delta psi is equal to minus 4 pi by lambda b into sine of A into cos b plus sine b into cos of A minus this original term. Now, you can see that delta theta is very small or approximately equal to 0. As a result, I have cos delta theta is equal to 1 and sin delta theta is equal to delta theta. We can write that this term, which is differential interferogram, is b will become sin theta and this will cancel with this term, and now I will have only this term where this becomes delta theta. So, I can write here cos of theta 0 minus alpha into delta theta. Now, you can see here this term is a correction term for the flat earth. I can write sin theta minus alpha is equal to plus correction term. So, which is cos of theta 0 minus alpha into delta theta. I hope you agree with that, and so I can write phase for the first and second acquisition with B1 baseline, and so I have sin theta 0 minus alpha 1 plus this correction factor here. I hope you agree with that. Similarly, for the first and the third acquisition, I can write this term with baseline B2 and this one, alpha 2 angle here and this one. One should note here that this term is coming because there is a difference in the range, and that happens because the topographic position of the point of interest has changed between the second and the third acquisition. This component is caused by the flat datum, and this is the component by topography in the both the terms, and this term is because of the change. So, this is again because of the flat datum and it is because of the topography. Here we can do one thing now. To understand the change in the topography, as we know that only this factor is contributing here, similarly only these two factors are contributing here. These factors can be ignored because they are coming from the flat datum of flat topography. So, let us consider these three factors 1, 2 and 3 in order to measure the change in the range or the change detection. We can write only the topographic term here for first term, and here for the second term we can write topographic term as well as the change term together like this. But the problem is we have different baselines. Because of the different baselines, it happens that there are two sensors, they are of different characteristics. Now we want to bring their measurements in one reference system or in one comparison frame so that I can compare their values. I will rescale the one with respect to the another. Generally, we have the term delta R in the first and third acquisition, and that is why we will rescale the psi 1 term. Note down that this is the topographic term here, which is this term, and here this is change term, which is here. What we want to do? We want to make this and these comparable so that we can determine this one. So, we do the rescaling. So, we find out what is the value of psi 1 new as with the old value, and then we do the rescaling with this factor. We know the theta 0. Now, we have done this derivation very clearly, but how to find the theta 0? We measure the theta, but we want to find out theta 0. So, what do we do here? We use a DEM that is already available. So, then using this range R, we project this point here and we find out what is the point A dash, and accordingly we find out what is the angle theta 0. So, this is the way we determine the angle theta 0 using the DEM which is already available. We know already theta 0, we already know alpha 2 from the sensor mechanism, alpha 1 from sensor mechanism, theta 0 from calculation, B1, B2 we already know from the sensor information. So, now we have done the rescaling. So, let us find out the phase difference between the two values here like this, and that will be equal to this value. So, any residual here, there will be different values after scaling also. So, any residual will be this value here, and this is the concept of differential interferometry. So, I hope you got the idea. What does it mean by the differential interferometry? Now, if we measure the delta R by measuring the residuals between the differential interferogram, because there are two interferograms, and now I am calculating the differential interferogram by delta psi here, or you can say delta of the delta psi. So, by this I calculate the value of delta R on the right hand side. So, that means I am measuring the residual, that is the final value that is given by the differential interferogram, and using that value I am calculating delta R, and that delta R will be the change in the range of the point on topography, because there was a change between the second acquisition and the third acquisition. That means, let us imagine that there is some change has happened within 1 year. So, second acquisition happened, and after 1 year of that, third acquisition happened, and during that time whatever changes are there, that will be reflected in the range delta R, or the change in the range R, and using that difference I can find out how point has shifted in the 3D position from original place to another place. So, this is the concept of the differential interferometry, and this is the use of the differential interferometry. Here the same expression of R2 minus R1 square. So, I can write R2 minus R1 square can be written as R2 minus R1 into R2 plus R1, and so this part is divided here for that remaining expression, and we have R1 plus R2 here. Now, as we said already that R2 plus R1 can be approximately 2R1 because R1 is approximately equal to R2. This will be cancelled out with this factor here, and finally I will have b here. So b into sine of theta minus alpha. What about this factor? Again it becomes 2r1, and again we see that b square by 2r1 is going to be 0 here. And as a result, now delta r is equal to minus b into sine theta alpha, and this is the baseline length parallel to the loop direction. And there, by this logic, we estimate the delta r for change detection. So what is change mapping? Change mapping is, I take the data for 1 and 2 pair, there is no change. But while I take the data for pair 1 and 3, that means in the third pass, during that time change has occurred. So if I take the baseline B2 between 1 and 3 sensor location, I can observe this change, and this change is indicated by this. So that is the application of the 3-pass interferometry, and 3-pass interferometry is basically meant for change detection only. I hope you got the idea. At last, we would like to tell you that in case of SAR data processing, there are many softwares are available, commercial as well as open source. So these are the lists here. So you can use anyone in order to do some kind of interferometry practices from the available data. So with this, I would like to finish this lecture. So far we have seen different aspects of the radar: geometric aspect, radiometric aspect, radar grammetry, and the interferometry aspect. Now finally, in the last lecture of this module, we will have the applications of radar for the geoscience perspective, or the geoscience applications of the radar. Thank you.